Hello everyone. For this video, I will be discussing the topic moment area method. It is a method of determining the slopes and deflections in beams which involves the area of the moment diagram. After a brief discussion, I'll answer a problem related to that topic. So, let's get this started. There are many methods for solving indeterminate structures. One of these is the moment area method, a very useful procedure for determining the linear and angular deflection of beams at specific points. This solution requires a combination of graphical and analytical approach. This concentrates on the moment diagram and its relationship with translation and rotation. Also, the moment area method relies on understanding its theorems. There are two moment area theorems, one that relates to the slope of the beam and one that relates to the deflections. These theorems provide a way to find slopes and deflections without having to go through a full process of integration. The first theorem states that the change in the slope of a beam between 2 points is equal to the area under the curvature diagram between those 2 points. For the second theorem, the vertical distance of point B on an elastic curve from the tangent to the curve at point A is equal to the moment with respect to the vertical through B of the area of the bending moment diagram between A and B divided by the flexural rigidity EI. Problem 9.98. For the uniform cantilever beam and loading shown, determine A, the slope at the free end, and B, the deflection at the free end. The first thing to do is to draw three diagrams: the free body diagram, the reference tangent diagram, and the bending moment diagram. From our free body diagram, we can determine the moment MB. We will write the equilibrium of forces in the y direction. Summation Fy equals to 0, By minus Wl equals to 0, and then By is equal to Wl. Then, summation Mb equals to 0, Mb plus Wl squared over 2 equals to 0, then Mb is equal to negative Wl squared over 2. Next, our reference tangent will be the horizontal tangent at the fixed end B. From the bending moment diagram, we can get slope B over A equals slope B minus slope A. Tangential deviation A over B is equal to deflection A minus deflection B. Since slope B and deflection B is equal to 0, our theta A is equal to negative theta B over A, and our deflection A is equal to tangential deviation A over B. So for letter A, we have here first the equation for area 1, which is derived from the bending moment diagram. So area 1 is equal to negative 1/3 times WL squared over 2EI times L. And then it results to area 1 is equal to negative WL cubed over 6EI. And since our slope B over A is equal to the area, our slope B over A will now become negative WL cubed and over 6EI. And since our slope A is equal to negative slope B over A, it will result to slope A equals WL cubed over 6EI. So the slope at free end is WL cubed over 6EI. And for letter B, we use the equation of horizontal distance 3L over 4, then substitute it to the formula of the tangential deviation. So tangential deviation B over A is equal to area 1 times the horizontal distance 1. So Negative WL cubed over 6EI times 3L over 4 results to negative WL4 over 8EI. So our deflection at the free end is equal to negative WL to the power of 4 over 8EI.